Okay, let's dive right into this. Welcome to this explainer. Today, we're taking a real journey, from the absolute surface of Python straight down to its core. Look, if you write Python, you use data types every single day, right? But honestly, mastering how Python actually manages memory and data models under the hood, well, that's exactly what separates the good developers from the truly great ones. Here's our roadmap for today. We'll start with the classification of data types, then look at the mutability factor, choosing the right container, nuances and limitations, and finally, common Python pitfalls. All right, let's get moving.
Section 1. Classification of data types.
So, before we start categorizing things, we need to establish the absolute foundational rule of the language. In Python, literally every single value is an object, and it consists of a type and a value, period. Now, Python groups these into specific categories. You've got your numeric types for math. Think of the integer 42 or the float 3.14. Then we have sequences. These are your ordered collections indexed by integers, like the string Aisha, or just a standard list. Moving on, we have mappings, like dicts, which are totally optimized for those lightning-fast lookups, and sets for unordered unique values. And of course, booleans for true or false, and the singleton none type to represent the absolute absence of a value. It's a neat, organized surface. But, let's look a little deeper.
Section 2. The mutability factor.
Because what we just looked at, that's purely the surface. We need to talk about mutability. This is the defining property of Python data management. It dictates whether an object's value can be changed in place or if a brand new object must be created in memory. Grasping this concept, it is the secret to moving beyond just memorizing syntax. It's what actually allows you to truly predict how Python behaves under the hood. Now, what's really interesting here are the hidden trade-offs. For immutable types, we're talking strings, integers, tuples. Once they're created, they cannot be changed. No way. So if you try to modify one, say by building a string in a loop using plus equals, Python isn't just updating it. It's actually creating a brand new object every single time. That is an incredibly costly O(n)² performance hit. On the flip side, mutable types like lists and dicts avoid that cost by modifying data in place. Sounds great, right? But they have a dangerous flaw: shared references. Meaning, changing a mutable object through one variable will unexpectedly change it for all other variables pointing to that exact same object.
Section 3. Choosing the right container.
So these underlying memory rules, they dictate exactly which container you should be using in practice. If I'm mentoring a junior developer, this is the hierarchy I absolutely want them to memorize. Python basically groups containers by how they access data, and that directly dictates performance. Do you need things in a specific order? Go with sequences. Use a list for dynamic collections or a tuple for fixed records. But if you just need to look things up super fast, use a mapping, like a dict. It uses unique keys and is absolutely ideal for JSON-like data. And what if you only care about uniqueness or just checking if something exists in a collection? Use a set. Choosing a dict or a set gives you O of 1, basically instant, lookups. And let me tell you, that is a massive, massive optimization over sequentially searching through a list.
Section 4. Nuances and limitations.
All right, this is where things get a bit tricky, as we peel back the next layer to reveal some real technical edge cases. And this brilliantly illustrates a couple of traps. First, dynamic typing. In Python, variables themselves don't actually have fixed types, only the objects they refer to do. This means type mismatches can easily hide in your code and will only crash at runtime if you aren't validating your inputs. Then there's truthiness. Every single object has an inherent Boolean value. Empty collections evaluate to false, but watch out, a string containing just a single blank space evaluates as truthy. It's a classic trap that catches beginners completely off guard when they're checking for user input.
Then we have to consider numeric precision. Python is incredibly generous with integers. Actually, they have arbitrary precision, meaning they can grow literally as large as your computer's memory allows. It totally saves you from traditional integer overflow errors. But, the trade-off is a silent performance penalty. Doing math on massive integers slows down your program because Python has to resort to multi-word arithmetic behind the scenes.
Okay, let me ask you a quick question. If you add the decimal 0.1 to the decimal 0.2, does it equal 0.3? Well, in Python, the answer is false. Crazy, right? So why does that happen? It's because of the IEEE 754 standard for floating point numbers. Simple decimals, like 0.1, actually cannot be represented exactly in binary. They create these tiny microscopic rounding errors deep in the math. So 0.1 plus 0.2 equals something ridiculous like 0.300000000004. It's an absolutely absurd limitation of binary representation, and honestly, it completely validates the frustration of pretty much every developer who has ever tried to write a simple financial calculation.
Section 5. Common Python Pitfalls. We are now entering the most dangerous territory of this explainer. These are the mistakes that quietly slip into production and completely crash systems. First up, equality versus identity. Beginners constantly confuse these two. The double equals sign checks if the actual values of the objects are the same. But the is keyword, that checks if two variables point to the exact same memory address. It's a huge difference. And here's the kicker. Because of an implementation detail called interning, using is might actually work by pure accident for small integers up to 256, but then it will suddenly, inexplicably fail for larger numbers. Never, ever use is when you just want to compare values. Here's another quick but potentially deadly trap, the built-in input function. It always returns a string. Even if the user types the number 5, it's captured as the string 5. Attempting math directly on that will instantly cause a type error. You absolutely must explicitly convert it using int or float. Knowing the exact type your functions return is just non-negotiable. Now, I really want you to pay close attention to this next one. Shadowing built-ins. Python will absolutely let you name a variable list, or str, or even print. I mean, it is completely valid syntax, but it is highly dangerous. If you name a variable list, the original built-in list function becomes completely inaccessible in that scope. You literally just destroyed your own access to a core Python tool. Hours later, you'll try to use the real list function and you'll trigger a highly confusing type error, all because of a bad variable name you chose earlier. So the crucial point is really testing your mental model here. We established earlier that tuples are immutable. Once they're created, they cannot be changed, right? So, can an immutable tuple ever change? Think about that for a second.
Well, the answer is a surprising yes, and it's all due to the tuple caveat. You see, a tuple freezes the reference to an object, not the object's internal state. If your immutable tuple happens to contain a mutable object, like, say, a list, you can still add or remove items from that inner list. The tuple itself still points to the same list in memory, completely satisfying its immutability rule, but the data inside that list has totally changed. It's a fascinating interaction between mutable and immutable rules that catches out even experienced coders all the time.
Which brings us to our final thought. The next time you sit down to write or review some Python code, I really want you to ask yourself, are you modifying data in place, or are you constantly allocating brand new memory without even realizing it? Because when you start seeing your code not just as syntax, but as memory references, allocations, and objects, that is when you truly master Python. Keep exploring, keep questioning, and I'll see you in the next explainer.